What if the biggest problem in artificial intelligence has nothing to do with intelligence at all? What if the real crisis is something much simpler, something hiding in plain sight inside every wire, every chip, every server rack on Earth? Before we go further, if you care about where technology is actually heading, not where headlines say it's heading, hit that subscribe button right now. Not later, right now. Because what you're about to hear sounds like science fiction, but it's already being tested in real labs, and it could change everything about how AI is built. Right now, somewhere on this planet, a company is pouring concrete for a new data center. It will be enormous, bigger than most airports. It will need its own power plant just to stay on. And when it's finished, engineers will proudly announce how many chips it holds, how much electricity it draws, how many billions of dollars it cost. But here's the strange part. Almost none of that massive size is about thinking. It's about moving. Most people assume AI is expensive because computers have to calculate so much. Numbers, predictions, patterns, all of that heavy math. And yes, that takes power, but that's not actually where most of the energy goes. Modern chips have become incredibly good at raw calculation. The real cost, the cost that is quietly bankrupting the entire industry's energy budget, is moving information from one place to another. Every time a piece of data travels from memory to processor, or from one chip to the next, it has to physically move through a wire. And that movement is not free. It costs energy. It costs time. And now with the rise of AI agents, systems that don't just answer one question, but plan, search, remember, check their own work, and talk to other AI systems, that movement has exploded. Think about it like this. A simple chatbot used to answer a question in one step. Now, an AI agent might search the internet, pull information from a database, run a calculation, double-check itself, store the result in memory, and then hand that result to another AI system to continue the task. Every single one of those steps requires data to move. Not once, but constantly, endlessly, across billions of transactions every second. And that's where physics stops being kind. Inside every chip, electricity moves through incredibly thin metal wires. As electrons travel, they bump into atoms in the material. This creates resistance. You can think of it almost like running through water instead of running through air. That resistance wastes energy, and that wasted energy has to go somewhere. It becomes heat. One tiny signal losing. A tiny bit of energy, as heat sounds harmless. But now multiply that by trillions of signals every second across a data center the size of a small city. Suddenly, a huge amount of the electricity powering the AI revolution isn't being used to think. It's being burned just to move information around, and then burned again to cool the mess it creates. For more than 50 years, the answer to almost every computing problem was the same. Shrink the transistor. Make it smaller. Pack more of them onto a chip, and performance goes up. This strategy worked so well for so long that it became almost a law of nature. But transistors can only get so small before you hit the actual size of atoms. And once you get close to that wall, shrinking stops solving the problem. In fact, shrinking starts creating new problems. More heat, more leakage, more cost. So the industry is facing an uncomfortable truth. The road that powered 50 years of progress is running out. And that means the next big leap in computing cannot come from a smaller version of the same idea. It has to come from a different idea entirely. This is where things get genuinely exciting. Imagine, for a moment, a material where electricity can flow with almost zero resistance. No friction, no wasted heat. That's not a fantasy. It's a real, well-understood state of matter called superconductivity. Certain materials, when cooled to extremely low temperatures, enter this state, and inside it, electricity behaves completely differently than it does in your phone or your laptop. Scientists have known about superconductivity for over a century. The idea itself isn't new. What is new is figuring out how to actually use it to build a working computer, one that could be manufactured, scaled, and eventually plugged into the systems already powering the AI world. Instead of relying on transistors, superconducting computers use something called a Josephson junction. The name sounds complicated, but the concept is simple. Picture a sandwich, two superconducting layers with a very thin barrier in between. When this junction switches, it releases an extremely small, extremely precise pulse. Scientists sometimes call it a single flux quantum. You don't need to remember that term. Just remember this. That tiny pulse becomes the basic unit of information, replacing the electrical signals your current devices depend on. And this is where the numbers start to sound almost unbelievable. A traditional transistor, switching in your laptop, uses roughly 500 millivolts of energy. A superconducting switch can do the same job using around 1 millivolt. That's not a small improvement. That's hundreds of times less energy for a single switch. And because the surrounding wires carry almost no resistance, very little of that energy is lost as heat along the way. Then there's speed. These pulses last about 1/trillionth of a second. That's 1,000 times shorter than the blink of a regular processing cycle. Your everyday computer runs somewhere around 3 to 5 billion cycles per second. Some superconducting circuits have already been tested running past 20 billion cycles per second, with some experimental versions crossing 100 billion. Numbers like that aren't just an upgrade. They represent an entirely different category of speed. Now, if all of this is starting to sound like quantum computing to you, you're not wrong to make that connection. But here's the crucial difference. Quantum computers rely on strange, delicate quantum effects like superposition and entanglement. They require entirely new algorithms and an entirely new way of programming. Superconducting logic doesn't ask you to reinvent computer science. It still performs classical computation, the same ones and zeros your current software already understands. It's just running on hardware built from a completely different physical foundation. That difference matters enormously. It means the industry doesn't need to throw away decades of existing software just to use this technology. And that alone makes the path from laboratory experiment to real-world product far more realistic than most people assume. So if the idea is this powerful, why isn't it already inside every data center on Earth? That question deserves an honest answer. Before we continue, let me ask you something. If this video is genuinely teaching you something new, do me one small favor. Tap the like button before you keep watching. It costs you nothing, but it tells me you actually want more videos like this one, and that keeps this channel going. For decades, superconducting computing stayed trapped inside research papers and university labs. The physics worked beautifully on a whiteboard. The problem was manufacturing. Building these devices reliably, at scale, in a way that made economic sense, seemed almost impossible. So while transistors kept shrinking and computers kept improving year after year, superconducting computing quietly waited on the sidelines. Technically real, but practically unusable. That changed when a research organization called IMEC decided to take a fresh look at the problem. IMEC is based in Belgium, and if you think of major chip makers as the factories where the future gets built, IMEC is more like the laboratory where the future gets discovered first. It's one of the few places on Earth working on technologies that might not become commercial products for another 10 years. And recently, IMEC turned its attention back to one of computing's oldest dreams. Not because the underlying physics suddenly changed, but because for the first time, the practical barriers standing in the way finally started to look solvable. Here's what they found. Instead of relying on older, harder to manufacture superconducting materials, IMEC used a compound called niobium titanium nitride. Unlike many earlier approaches, this material can actually be built using processes similar to standard chip manufacturing. These devices can be produced on the same 300mm wafers, already used across the semiconductor industry. That detail might sound technical, but it's actually one of the most important parts of this entire story. It means, for the first time, superconducting computing has a realistic, believable path toward mass production, instead of staying locked inside a handful of specialized labs. But the real breakthrough is hidden inside the tiny barrier at the center of the Josephson junction, the thin layer sitting between the two superconducting materials. For years, that barrier was one of the biggest obstacles preventing this technology from scaling. IMEC replaced the traditional material used there with something called amorphous silicon. It sounds like a small technical swap, but it dramatically improves how reliably these devices can be manufactured at the density needed for real, functional computing systems. Now, here comes the obvious objection, and it's a fair one. All of this only works at extremely cold temperatures. We're talking about roughly 4 degrees above absolute zero, colder than deep space. You cannot simply slide one of these chips into a normal server. It has to sit inside a highly specialized cooling system called a cryostat, essentially an advanced scientific refrigerator built to hold temperatures almost at the coldest point physically possible in the universe. So the obvious question follows. Doesn't all that cooling just cancel out any energy you save? For something small, like a laptop or a phone, the answer is yes, completely. Cooling a tiny device to near absolute zero would cost far more energy than it saves. That's exactly why you will never see this technology inside your personal devices. But scale changes everything. According to IMEC's own research, there's a tipping point. Below a certain size, cooling costs more than it saves, and the whole idea falls apart. But once you reach the scale of a modern AI data center, the equation flips completely. At that scale, the energy saved from eliminating resistance and wasted heat becomes dramatically larger than the energy spent on cooling. In other words, this technology doesn't make sense for small systems. It makes enormous sense for massive ones, exactly the kind AI companies are building right now. And there's a second advantage that might matter even more than energy savings: density. To understand why, picture what a future superconducting computer might actually look like. At its core sits a processing unit similar in role to today's most advanced AI chips, but most of it lives submerged inside liquid helium, sitting at around 4 degrees above absolute zero. From there, a thermal bridge connects it to a slightly warmer zone, still bitterly cold, but warm enough for conventional memory chips to operate efficiently. Beyond that sits the normal room temperature world we live in. In a strange way, it's a single computer built across 3 completely different climates. Here's why that structure matters so much. For decades, chipmakers improved performance by making transistors smaller and smaller. But now that shrinking has hit its physical limits, the industry has been forced to grow in a new direction, upward, stacking chips on top of each other instead of side by side. The problem is heat. Modern processors already struggle to cool a single flat layer of silicon. Stack multiple layers of active logic directly on top of each other, and the heat trapped in the middle has nowhere to escape. Eventually, the chip essentially cooks itself from the inside. That's why today, engineers mostly stack memory on top of logic, not logic on top of logic, because stacking heavy computation directly together would overwhelm any cooling system. Superconducting circuits change that entire equation because they generate so little heat in the first place. Suddenly, stacking logic directly on top of more logic becomes physically possible. Layer after layer of processing, power packed tightly into a dense 3-dimensional block. Shorter distances for data to travel, higher bandwidth, far less wasted energy. And this is where the numbers become almost hard to believe. IMEC modeled a future system built from just 100 superconducting circuit boards. Their projection suggested this system could fit inside something roughly the size of a shoebox, while delivering more than 20 exaflops of computing power. To put that into perspective, that's roughly 20 times more raw computing power than today's largest supercomputer on Earth, a machine that currently fills an entire building. And the power consumption for this shoebox-sized system? Around 500 kilowatts. Compare that to modern AI data centers, which consume hundreds of megawatts, sometimes requiring dedicated power plants just to stay operational. If these projections hold up in real-world testing, we're looking at potentially over 100 times better energy efficiency, packed into a footprint thousands of times smaller than what exists today. This is genuinely where that headline number comes from. Not science fiction, not exaggeration. A real research projection suggesting that the physical space required for enormous amounts of AI computing could shrink dramatically, from something spanning the size of dozens of football fields down towards something that could realistically sit inside a single room, or eventually something even smaller. Let's pause here for a second, because I think this deserves real attention, not just excitement. If you've made it this far, I want you to do something a little different than the usual subscribe reminder. Leave one word in the comments describing how this makes you feel about the future of AI. Excited, nervous, skeptical, amazed, anything. I genuinely read these, and I want to know what's going through your mind right now. Now, it's worth being honest about something important. IMEC's breakthrough is not the only serious attempt to solve this problem. Other major players in the semiconductor world are exploring their own radical approaches to the same underlying issue, the cost of moving information inside modern computers. This tells you something significant. The entire industry has quietly reached the same conclusion at roughly the same time. The old path is running out, and multiple serious organizations are racing to find whatever comes next. Here's something else that connects to this story in a way most people don't expect. Right now, there isn't a dedicated factory anywhere in the world built specifically to mass-produce superconducting logic chips. At least, not yet. But the technology world is already investing enormous amounts of money into something closely related: quantum computing. Major companies are currently building massive new manufacturing facilities dedicated entirely to quantum technology. At first glance, that seems completely unrelated to what we've been talking about. Quantum computers and superconducting classical computers are fundamentally different machines, built for different purposes, but underneath the surface, they share something crucial: the same engineering challenges. Both rely on superconducting materials. Both require cryogenic cooling near absolute zero. Both need highly specialized manufacturing processes and electronics capable of functioning reliably at extreme cold. In other words, every dollar spent building a factory for quantum computing is quietly solving many of the same manufacturing challenges standing in the way of superconducting classical computers. For decades, this entire field faced a frustrating standoff. Nobody wanted to invest in manufacturing infrastructure because there weren't enough real products to justify the cost. And there weren't enough real products because there wasn't the manufacturing infrastructure to build them. It was a closed loop with no clear starting point. Now, thanks to the massive investment pouring into quantum computing, that loop is finally breaking. For the first time in history, there's a serious, well-funded, industrial effort to build computing hardware that operates just a few degrees above the coldest temperature physically possible in the universe. And that effort, even though it's aimed at quantum computers, is clearing the path for superconducting classical computers to follow right behind it. This is really the heart of why this story matters so much. Artificial intelligence has exposed a bottleneck that used to hide quietly in the background of computing. Distance. The physical distance information has to travel inside a machine. Heat, the energy wasted every time that information moves. And power, the sheer scale of electricity required to keep it all running. Superconducting logic attacks all three of these problems at the exact same time, not by building a slightly better version of the transistor, but by fundamentally rethinking how information moves through a computer in the first place. To be clear, this technology is not going to replace the chip inside your phone or your laptop anytime soon. Silicon-based computing will remain the foundation of everyday consumer devices for a very long time. This shift is happening at the extreme edge of computing, inside massive AI systems and future quantum machines, where the sheer scale finally makes the trade-offs worth it. But here's the part that I think matters most, the part that goes beyond chips and cooling systems and technical specifications. Once moving information becomes dramatically cheaper, something bigger starts to happen. Computing power no longer needs to be crammed into a handful of massive, centralized facilities, each one demanding its own power plant just to stay running. Instead, computing can become denser, smaller, more efficient, and placed much closer to where it's actually needed. Closer to factories, closer to power grids that can actually support it, closer to the real world instead of hidden away inside distant industrial complexes most people will never see. That shift from massive and centralized to compact and distributed might end up being far more important than the raw performance numbers themselves. For 50 years, the story of computing was about making things smaller, one transistor at a time, one generation at a time, quietly reshaping the entire world. Now, we may be standing at the very beginning of a new story. Not about shrinking a single component, but about shrinking an entire concept, taking something as massive and power-hungry as a modern AI data center and asking a question that would have sounded absurd just a few years ago. What if all of that could fit inside a single room, or a single refrigerator, or one day, something even smaller than that? Nobody can promise exactly how this story ends. Manufacturing challenges remain. Cooling infrastructure needs to scale. Real-world testing will reveal problems. No lab model can fully predict. But for the first time in a very long time, there's a real, credible, physically grounded path towards solving one of the biggest problems facing artificial intelligence. Not by building faster chips, but by rethinking the very foundation computing has stood on for the past 100 years. And if that path holds up, the next great leap in artificial intelligence might not come from a bigger data center at all. It might come from one small enough to fit in a room you could walk into.